Let's get this show on the road. Hello, everyone. Hope you're well. Okay. All right. Good. Okay. How's it going? Hope everyone's well. Yeah. Natalie, are you in like a library or something?
Yeah, I'm in the library. It looks like it's a backdrop though, like something I like one of the
Yeah.
green
Yeah.
screens,
Okay.
but it's actually the library.
All right. Well, all right. Let's get into it. So last time we introduced partial fractions. Let's actually do a quick recap here. So we went through all that stuff, showed some cool things, how to actually do the partial fractions. We're going to do a lot more examples here, but let's actually just do a recap what we have seen, what we have learned, to make sure that we're all on the same page. So last time we did partial fractions. So this is just the idea of breaking up larger fractions into smaller ones. Smaller / more manageable. Okay, and it had a process. So first thing, 0, you need to make sure fraction, and I don't know, fraction is kind of simplistic, more like a rational function. Instead of fraction, let me be specific here and say rational functions. So you do want to have a ratio of polynomials. That's where it's gonna work. So you need to make sure that the rational function is proper. And the denominator is factorable. So let's say you are approaching an integral. It is the integral of a rational function, and you realize that, yes, it is proper, but the denominator doesn't factor. Then you can't actually use partial fractions. You would have other options, like if it's a quadratic, you try completing the square and do a trig sub, or maybe some other kind of substitution. But you really need, for this thing to even work, for it to be even an option, it should be a rational function, and you should be able to factor the denominator. So once you know that these guys are true, and of course, if it's not proper, you can make it proper. We showed you that last time through long division or like some sort of algebraic manipulation. Then what you do is you'd factor the denominator. To break into fractions based on the factors in the denominator. With two things. One, you want a generic numerator. Specifically 1 degree less than that of the denominator. And two, you have to count up to repeated factors. Count up to the multiplicity of repeated factors. So that covered the case that we saw earlier, or last time. Where was it? So like here, where you saw this factor got repeated because of the square. So there are 2 of those x squared plus 1 factors, you have to do 1 to the first power, then 1 to the second power. When we have the x plus 1 cubed, you think of that as 3 factors. So the x plus 1 has a multiplicity of 3. You have to actually count up to the multiplicity. So x plus 1 to the first power, x plus 1 to the second power, x plus 1 to the third power. And the numerator is some generic polynomial, 1 degree less than the base factor. So when you're talking about the numerator of each of these, you're looking at the thing that's inside the parentheses. Okay. And 3, find, if required. So sometimes, especially on quizzes, I might just test you to see, do you know how to break something up? But let's say you fully want to solve a problem, you fully want to get the integrand in a nice form for you to actually find an answer. You do need to find the coefficients of the numerators. Using one or both. You can mix them. Okay, so one method was once you write something with the breakdown, you multiply both sides by the denominator of the big fraction. This will clear all denominators, and then you plug in convenient values of x to solve for the arbitrary constants. The most convenient values are the values that will cancel all the arbitrary constants except 1, but sometimes this is not possible. You can just plug in a bunch of values where you have several arbitrary constants present, and then you develop a system of equations from that. That's also doable. The second option is to actually expand all the parentheses, group the like terms of the variable, and equate coefficients, and you would develop a system of equations from that. So there is a start. Sometimes we can use the cover-up method. And this works, just to remind you, the cover-up method doesn't always work. It works for non-repeating linear factors or the highest multiplicity of a linear factor. Okay, so what does that mean? Let's say, and I mentioned that I would actually talk a little bit more about the cover-up method today, and then we're going to get through these examples. Hopefully you guys tried them, so we should be able to make quick work of them in a bit. But I just wanted to slowly go through partial fractions. I feel like we rushed it a lot last time, so I just want to make sure that everyone's kind of on the same page, which is why it's also kind of why I'm like writing all these steps down by hand, even though I already typed up all these steps earlier. It's just to kind of actually manually slow down the pace so that you guys are, I'm making sure that you guys are absorbing everything. Okay, so as for why the cover-up method works, let's actually look at that. Why the cover-up method works. Okay, so I can show you with an example. I'm not going to like do a general proof or anything like that. Suppose we have, say we have 4 over x minus 2 times x minus 3, for example. Okay, you would break this up into a over x minus 2 plus b over x minus 3. Now, what you can do here is if we multiply by denominator of a, we would end up with this kind of situation. So I multiply both sides by x minus 2. That's going to cancel that. And the b will have that. Now what you notice is that if we plug in what makes the denominator of a 0, here clearly that's going to be x equals 2. Here's what would happen. I would actually obtain 4 over 2 minus 3 equals a plus b times 2 minus 2 over x minus 3. So you see that this part here is going to go to 0, and I'd be left over with a, right? Now, what I want you to notice is that this part here is what we get if we covered up the x minus 2 and plugged in 2 in the original left side. So sometimes people ask, well, why would I plug in what would make the denominator of a equals 0? We don't want denominators. Well, technically, you're not making the denominator 0 because you're multiplying through by a specific factor in the denominator. And then when you plug in what makes that factor 0, it will wipe out everyone else. And it would just leave the variable that had that denominator. If you have something like a repeated factor, so you can do the same trick. A similar trick would work for b. Let's say you had a repeated linear factor. Let's say you had 4 over x minus 2, and let's make that squared, and x minus 3. This would break down into a over x minus 2 plus b over x minus 2 squared plus c over x minus 3. I probably should have asked you guys to break that down, but I will have examples later. And what would happen now is, let's say I wanted to find the numerators of the guys with the x minus 2s. It's not good enough to multiply through by one of the x minus 2s, because then if I have a x minus 2 left over on the left, what's going to happen is I can't plug in what makes that 0 because I would divide by 0. I have no choice but to actually multiply by the highest power, multiply by the x minus 2 squared. Then that's going to leave me with 4 over x minus 3 equals a times x minus 2 plus b plus c over x minus 3 times x minus 2 squared. Now if I plug in the x equals 2, notice that everyone gets wiped out except the guy that had the x minus 2 to the highest power in the first place. So I could actually use the cover-up method to find the b. Four over 2 minus 3 is going to be b. So this means that my b is minus 1. I actually can't use the cover-up method to find the a because I would need to multiply by x minus 2 in order to do that, but that would cause a division by 0 on the left side. So this trick works for linear factors or the highest multiplicity of a linear factor, okay? And it kind of works because of this simple reason. Turns out in a class called complex analysis, you'll actually learn a general theory that can even expand on this called the residue theorem, but that is way above our pay grade, where this is actually a special case of that theorem. But it turns out that for very simple algebraic reasons, you can see why such a method would work. So last time I introduced this idea of whenever you have repeated linear factors, you can literally just like take your finger and cover them up and plug in the x values that would make that guy 0. And that will actually give you the value of the numerator of that linear factor, which is really cool. It's very quick. It's a nice shortcut. And a lot of times it allows you to do a partial fractions literally in your head. So while your friend is over there beside you, either doing method 1 or method 2, and they're taking forever solving systems of equations, you can actually just look at the value and know what the answer is just by looking at it. They're going to like, well, how did you know that so fast? Like, got to study as hard as me, son. You know, you can like kind of show off, but yeah. Okay. And that's true with almost any mathematical trick. It's never magic. It's just that the person knows something that you don't. But I thought I'd show you that trick because it comes in handy pretty often, actually. So that is mainly partial fractions. I mean, we need to go through method 1 and method 2, but we'll see examples here. But this is the overall strategy. It is used when you have a rational function, which is a ratio of polynomials, and the denominator factors, and it is proper, right? You can't really turn a denominator that doesn't factor into one that factors. So if the denominator doesn't factor, all bets are off. You need a different method. If the denominator factors, but it's not proper, you can use long division or something else to make it proper, and then you're off to the races. Factor the denominator, break everyone up based on the factors of the denominator, make sure that they all have generic numerators 1 degree less than the base factor, and you can use one or both of the methods that I described in the last class to actually find the numerators. And sometimes whenever you're dealing with linear factors or the highest multiplicity of a linear factor, you can do the cover-up method. Saves you a lot of time. So that being said, that's our recap for those of you who may have been a little lost last time. Let's actually just run into some examples. So some of these examples are a little bit harder than I would actually ask you to do in practice. So I'm kind of going to skip them because I just don't want to waste time on it. So I am going to do example A and D with you guys. Hopefully you guys try B and C. It's good practice to do it anyway. And it's easy to actually check your answers. So once you actually do a partial fractions, remember what your answer is supposed to be equal to the original. So if you broke something up into a bunch of fractions and you add those fractions together, you should actually get the original fraction. If you don't, then you did something wrong. You could also check on Wolfram Alpha or something like that as to whether or not you did the partial fractions correctly. So either way, you'd be able to check your work. But just for the sake of the demonstration, I want to do these two. So in example 1, I'm going to do parts A and D, and then we're going to go through all these integrals. That being said, I did actually want you guys to try these on your own, and hopefully you did. So this is going to be another segment of the class where it's mostly audience participation, hopefully. And at that point, maybe we'll like get an idea of some of the things that people are struggling with, what they understand versus what they don't understand, etc. So let's actually focus on the first one. Okay. Go. This is you guys.
So first what I did was I factored the denominator and I did x times x plus 1 squared.
Yep, that actually works. So you have the denominator factors. So this is equal to, still in green, 5x squared plus 20x plus 6 over x. Factor of the common x, you'd have x squared plus 2x plus 1, and that factors into x plus 1 all squared. Now, it's important that we did check 1. This is a rational function. 2, it's proper, right? The degree on the numerator is 2, the degree on the denominator is 3. You want the denominator to have higher degree than the numerator, and 3 denominator factors. Right? So these guys are important for partial fractions. All bets are off if you don't have these things. So that's just a reality check for you. Partial fractions. That was totally messed up. the thing that is most insurmountable, well, I mean, specifically rational function and denominator factors are the biggest issues. If it's not proper, but the other two work out, you can fix it. But it turns out these first two, you can't really fix it. If it's not rational in the first place, then you're kind of out of luck. Or, I mean, technically, you can have something that's not rational, but with a substitution, you transform it into something rational. We've done that before. So that's when something like a u squared substitution might come in handy. So maybe there's something that's not a rational function when you look at it, but you do like a u squared substitution or u cubed substitution, and you transform it into something that you got rid of the radical, and now partial fractions becomes a possibility. I would tend to think of that, though, first as a substitution example first, and then as a partial fractions example, but hopefully you guys get what I'm saying. You have to have a ratio of polynomials to get this to work, and the denominator have to factor. Maybe you might have to do a substitution to get into this situation, but you have to know that you're in this situation before you even try this. Okay, so I do want to emphasize that. If you don't have these three things, you cannot do partial fractions. It's not going to work. You'll waste your time. Okay, all right, so very long-winded, but we're going to pick up speed as we go on. Yeah, how did you continue once you have that?
So then what I did is I did a over x plus b over x plus 1 plus c over x plus 1 squared. So then I did the cover-up method to find.
Just some commentary here. So remember, each of the factors of the denominator are x is a factor in the denominator, and x plus 1 is a factor. These are the base factors. You're going to break into smaller fractions based on these factors, right? The numerators must be 1 degree less, exactly 1 degree less than the highest power of these base factors. So in the first case, x, the highest power is 1. So your numerator needs to be power 0. Second case, x plus 1, the highest power is 1. Your numerator has to be degree 0, meaning constants. When it comes to x plus 1 all squared, that's a repeated factor. It has multiplicity of 2. You count up to the multiplicity. Okay. All right. Keep going.
Okay, so then I did the cover-up method to find a.
Okay.
So I plugged in 0, and I got a equals 6.
So this is 6 over 0 plus 1 squared. A equals 6 by cover-up method. Maybe I should put this in another color. So by cover-up method, what would we look at for cover-up method? Well, we look at the 5x squared plus 20x plus 6 over x times x plus 1 squared. What we do is we take our finger, we cover up the x, and then we plug in what would make that 0, which namely is x equals 0. You would get from that 5 times 0 squared plus 20 times 0 plus 6 over 0 plus 1 squared. And hence we have that answer. So a equals 6. Okay, then?
So then I also did the cover-up method for c. So what I did is I covered up the x plus 1 squared on the bottom, and then plugged in -1 for all the x's, and I have c equals 9.
Okay.
So then
5 plus 6, which is 11 minus 20, which is minus 9 divided by 1. Yeah. Yeah.
So after I got A and C, I had to get B, but you can't use the cover-up method for that one. So then what I did is I multiplied both sides by the denominator.
What did you get on the left, on the right?
So I did 6. I just plugged in A and C into initially. So I have 6 times x plus 1 squared plus b times x plus 1, and then plus 9x.
Right. So these are the A and the C values found previously. You just plug them in. Okay.
And then you could just choose any random number here. So I just chose 1.
Sure. So if you plug in x equals 1, we would get 31. And so what we would get here is 1 plus 1 squared. That's 4 times 6. That's 24 plus 2b plus 9.
And then I got
Yeah.
b equals -1.
So this means that our original guy, this guy here, that was it's more effort than I wanted. I think it would have been faster if I just wrote it down. Okay, yeah. So that's equal to a, which is 6 over x plus b over x plus 1, but your b is -1, plus c over x plus 1 squared, and our c is 9. All right, and you can check if I were to add all the fractions on the right side, they would actually combine to give me the fraction on the left side, or the rational function. Okay, so we went through that one very slowly just to make sure everyone has the technique down. Are there any questions at this point? Anyone unclear about anything? I think this one problem actually showed almost everything. I mean, the only technique that we didn't do was the expand and equate like powers technique, but I think that one is also kind of. So are we good?
Good.
Okay. All right, let's move on and let's actually try to speed things up. So let's do D. Okay. All right, someone else tell me. Let's get a move on.
I added one and subtracted one on the top so that I could factor it into, or not factor it, separate it, I guess, into 1 plus 1 over x squared minus 1.
Yep. Then?
And then from there, I separated that term into 1 over x plus 1 times x minus 1. And then I did the decomposition for that to get a over x plus 1 plus b over x minus 1. And then there I just used the cover-up method to find that a equals -1/2 and b equals 1/2.
Right. And you don't even have to even write down the a and the b. You could literally write on the line, just actually write these down by like covering it up with your finger. Cover up the x plus 1 with your finger, plug in x equals -1. You would get -1/2. Cover up the x minus 1 with your finger, plug in x equals +1, and you get +1/2.
So on a problem like this, if we were to have to like turn in work for something, it would be all right if we didn't write the a and b while doing the decomposition?
Yeah, if you're using something like the cover-up method, yes. Like if it's something where you have to like set up a system of equations to solve for, I expect to see you go through that.
When you're
For the
using the
cover-up
cover,
method, yeah.
when you're using the cover-up method, like in the denominator, so like the one you're covering up is the one you cover up in the like initial equation, and then you use the number that makes the one you're covering up 0 for the other terms.
Yes.
Okay.
So when I care about the numerator of the x plus 1, I will go to the original, cover up the x plus 1, and plug in what would make that 0, namely x equals -1. When I care about the numerator of the x minus 1, I cover up the x minus 1 and plug in x equals 1. Right, and there's like I said, I showed you the reason why this works earlier. There's actually a much larger theoretical reason why this works, but it's actually way above the level of this class. So that's all I'll say about that. Yeah. Okay, now let's do some integrals. Okay. All right, go. I think I put a problem similar to this on a quiz before. Maybe it wasn't a bonus or something. Who did this one?
I did. I couldn't exactly see how to get it to be proper, so I did long division and
Okay.
ended up getting 1 plus x plus 5 over 4x squared minus 4x minus 3
1 plus x plus 5
over
over
4x squared minus 4x minus 3.
Okay, so I mean, that's fine as long as you can do that. How you would do it here, though, just for interest's sake, the trick is, like last time, try to get the denominator in the numerator. So for example, the denominator says 4x squared minus 4x minus 3. So what I would do is I would put in that minus 4x minus 3. But then, of course, I have to subtract that. I have to add back the 4x, add the 3, right? So I'm not changing anything. And that last part you can do in your head. You can just add it to 2. But the idea is I want the numerator, I want the denominator in the numerator, right? So I add and subtract whatever I need to actually get that in the numerator, right? So now what's going to happen is the first part, this part here, is going to combine to give me a 1.
I have a quick question. What happened to that
And then
negative 3x on the top?
I
Is
missed
it-
it.
Okay.
So I subtracted 4x, subtracted 3, and I add the 4x, add the 3 so as to not change the value. I just put it in the middle of these things. Now what I have left over is the 4x minus 3x, which just leaves me with an x. And the plus 3 plus 2, that leaves me with the 5.
Professor,
Yeah. And
Is
so
there a way-
you get the same thing.
is there a way that you could also just do like minus x minus 5? Or no, because like that's a whole, like that's one term.
Minus x minus 5 where?
Like on the numerator, and then like do the plus x plus 5 somewhere else, because if you subtract 1x, you get 4x, and then if you subtract 5, you get negative 3, instead of doing like a whole, like two
Yeah,
terms.
but you'd have to account for that. So if you subtracted an x, you'd have to add an x.
Right. Okay. So then that's how you
So
get the x plus 5.
you could look at this as, oh, let me subtract an x, and then I'll have to add an x, and then let me subtract a 5, so I'll have to add a 5. Then the x and the 5 that you added is the new numerator. Notice that we have
Right.
x plus 5.
Okay.
Yeah.
Thank
So
you.
a couple ways to think about it. But the idea is you manipulate it in such a way that you get the denominator in the numerator. Now, if that confuses you at all, it's fine. You can still just fall back on long division. It's a lot less, you need a lot less insight to get the long division to work. The long division is very algorithmic, very systematic. So if you don't even get what I'm saying right now, it's actually okay. Just do the long division. If you're very quick with it, it shouldn't actually take too long to do the long division. Okay, so now we're here. Now what?
I factored the denominator into 2x minus 3 and 2x plus 1, and then split that up into partial fractions. So I had a over 2x minus 3 plus b over 2x plus 1.
And what are the numerators here?
A, I got to be 13/8 and b, negative 9/8.
Okay, and again, you could use cover-up method here, right? 2x minus 3 as well as 2x plus 1 are linear. So you could cover up the 2x minus 3. So cover up. So I could take the x plus 5 over, say, 2x minus 3 times 2x plus 3, and I can cover this up, plug in x equals 3 halves, and I would get 3 halves plus 5 over 6. Can multiply top and bottom by 2. I would get 3 plus 10 over 12. You said 13/8?
Yeah. I may have just done it wrong though.
I think you wrote 2x plus 3 instead of 2x plus 1 in the little like side word.
Oh, okay. So it's me. And so this should be a 4 here. So that should be an 8 there. And so that's your 13/8. And that's what you can put here. And again, you can do cover up here as well. Okay, now that you have that.
What I did is I split that up into 3 separate integrals so I could pull the coefficients off of the fractions to make it easier for myself.
Yeah. And then what?
And then I integrated
Integral of 1.
x.
And the integral of the other one?
I got 13 plus ln absolute value of 2x minus 3 all over 16.
Ln of absolute value 2x minus 3, and you'd have to multiply by a half because of the substitution. Pull out the 9/8. This gives you ln of absolute value 2x plus 1. You have to multiply by a half because of the substitution. And so you get x plus 13 over 16 ln of 2x minus 3 minus 9 over 16 ln of 2x plus 1.
Professor?
Where did
Yes.
that?
Oh, I was just gonna ask where that 1/2 comes from. I don't know if that was the same question.
Substitution, right? U equals 2x minus 3. Your du would be 2 dx. So 1/2 du equals dx. Then the integral would become 1/2 the integral of ln u, 1/2 the integral of 1 over u, which is ln of absolute value of u. So the 1/2 comes from the substitution. So if you wanted to integrate, say, 1 over 2x minus 3 dx. And this goes back when I was talking about substitution. The idea was if your substitution is a linear term, you just divide by the coefficient. So what you would do here, technically speaking, is this. Your du would be 2 dx. You'd have 1/2 du is equal to dx. And so your integral would become that. And so you'd have that 1/2 ln of u equals 1/2 ln of 2x minus 3. And that's what goes here. Or just know u is linear. So divide by a leading coefficient. So that's something that we mentioned a while ago. So if your u equals ax plus b, then you're always going to have a 1 over a times the integral with respect to u. Okay.
So if it was 1 over 4x plus 3, it would be 1/4 times 1 over u?
Right. And so if I have 1 over 4x plus 3, the integral is going to be 1/4 ln of absolute value 4x plus 3.
Okay, thank you.
it's something that students forget quite often. If you look back in the syllabus, you'll notice I even mentioned that. Okay, this one?
So
Oh, wait, was that? No, I did not mean to do that. This is one of the ones that I wanted you guys to work on your own. My thing is acting up. Okay, let's keep going. Okay, B.
So for this one, I wasn't really sure, but I thought that I could do a U substitution.
What's your U?
I think radical X.
So you could do that. I mean, there are nicer ways to do this as well. What you could also do here is just do a square both sides. It'll make it easier to see how things plug in. Differentiate. So your dx becomes 2 du. Your radical x, well, that's u. And your x is actually u squared when you plug everyone in. So this part here becomes your 2u du. This part here becomes your u. And this part here becomes your u squared. So now you actually end up with 2 times the integral of u squared over u squared minus 4. How do we deal with that?
So then what I did is I subtracted 4 and then added 4 on the numerator. And then it gave me 1 plus 4 over u squared minus 4.
Okay.
And then it's, 1 plus a over u minus 2 plus b over u plus 2 because it's a perfect square.
Right. So this part here is just 4 over u minus 2 times u plus 2. How did you get the coefficients?
Oh, so I did the cover up method again. And I think that a is 1/4. And
well,
b
you
is
cover up the
negative.
u minus 2 and then you plug in 2. So that will actually give you 1.
Oh, because the 4 is on top.
Because there's a 4 on top.
Right.
Then you
So then
cover
it'd
up
be
the u
-1.
plus 2 and then you put minus 2 and then that's -1. So now you integrate 1 du is integral.
Oh, u.
This integral.
1. Oh wait, you have to take anything out because there's no a, right?
Right.
Okay, so 1. Oh wait, no 1/4. ln times u minus ln of u minus 2 absolute value minus ln of u plus 2 plus c. And then you plug in radical x for the u.
So that was 1. So this is an example where originally we were not given a rational function. I want you to notice that because the radical x is there, this was not rational, right? So you couldn't actually do your partial fractions idea. However, with a substitution, we now transformed it into a rational function. It transformed into a rational function that was not proper though. So we first had to do our algebraic manipulation to actually transform that into something proper. So we subtracted 1 and added 1. Subtracted 4 and added 4. And then that allowed us to break it into 2 parts. The second part now is a rational function that's proper. The denominator factors. I can do partial fractions on that. Cover-up method. I can pretty much do it in my head. And then after that, the integrals are not so bad. This one.
Here I went ahead and did a u substitution where u equals e to the x.
So you ended up with that, yeah?
Yeah.
Okay,
So
now?
then I split that up into au plus b over u squared plus 1 plus c over u minus 1. And then I used the cover up to find c, which was 1/2.
Right, now we focus on this part here. So we have 1 over u squared plus 1 times u minus 1 equals au plus b. We know that c, I can find that by the cover-up method. So this is 1/2 by cover-up. Okay, and what did you do to find the others?
I multiplied out the denominator and then did that equate the coefficients thing.
Okay, so you multiply it out. So you have au squared minus au plus bu minus b plus cu squared plus c. And of course, we know what the c is. We'll plug that in eventually. Then you can group these. So it's au squared plus minus a plus b times u, a plus cu squared. And then you have minus b plus c. Yeah? And so what could you get from that?
I got the a equals negative 1/2 and b also equals negative 1/2.
Yeah, but give me the system.
I put 0x squared plus 0x plus 1/2, and then I plugged in c, so I had that a plus 1/2 would have to equal 0. And then
Yeah,
I
the
plugged
other
that,
one?
and then I plugged that into my b minus a and found that b also has to equal negative 1/2.
And then we had that the minus b plus c must be 1. So here, your a would have to be minus 1/2 since c equals 1/2. Since your a is minus 1/2, your b is also minus 1/2. And so now you have all those guys. So you can go back to the original. So your a was minus 1/2. And your b is minus 1/2. And your c is plus 1/2. Looking okay so far?
Yeah, that's where I was.
Okay, and now what?
I went ahead and broke that up into 2 integrals again, just so I could pull both the coefficients outside.
Okay.
So I had negative 1/2 u plus 1 over u squared plus 1 plus 1/2 the integral of 1 over u minus 1.
Okay. And then what did you do with the first one?
I don't know if this is right, but I did like a t substitution with u squared plus 1 equals t.
Right away?
Yeah. I mean, it got
I mean,
me
that's
there.
fine.
I just had to back substitute twice.
I would break this up further though. Right? Because your substitution would only work on the first part. Do you see that? Because when you do a u squared plus 1, your du is just going to be 2u, which means your plus 1 in the numerator is actually out of place. However, if I split it up, then I can do a substitution here. So like a t equals u squared plus 1 substitution. And eventually I would get that this would just be 1/2 times ln of u squared plus 1.
No, you're right. I did that. I didn't see it on my work. I confused that integral with the next one.
Okay. Right? What is this one?
Inverse tangent.
Tan inverse, right? So this is minus 1/2 tan inverse. So that's just a basic formula. And this one?
1/2 ln u, absolute value of u.
Mm-hmm. And again, that's a semi-basic formula. And so now you can go in and we can plug in our u's. Our u's was what? Was this e to the x? So this is e to the 2x plus 1 minus tan inverse of e to the x plus 1/2 ln of e to the x minus 1 plus c.
Professor,
Yeah.
could you go back to after you equated the equations and then how you split up these two integrals into 3? A little farther down in that.
So you're okay with up to here?
Yeah.
Oh, you mean here?
Yeah, like, and then also the backwards, like the t substitution too.
Okay. Let's make some space here. All right, so what we did was 1/2 is a common factor, right? The minus 1/2. So if you factor out the minus 1/2, you'd have u plus 1 over u squared plus 1. And over here, we'd have this. Right? Now I realize that this is a new integral, so I go through my process again. Is it a basic rule? Can I simplify it to be a basic rule? Would a substitution work? It turns out that it's not a basic rule, can't simplify it to be a basic rule. As for the substitution, I would want to substitute the denominator. However, that plus 1 is now out of place, right? Because if I do if I do a t equals u squared plus 1, my dt is actually 2u. So what I would do here is split this further to get the substitution to work on one part, and then I'll deal with the other part separately. And over here, if I do a t equals u squared plus 1, my dt is going to be a 2u du. And so I end up with minus 1/2 times 1/2, 1 over t dt, which becomes ln of t, and my t here is u squared plus 1, hence I get that.
Thank you.
Okay. This one.
So, I thought that you could treat it like any other one. So I did the integral of a over sine x plus b over sine x minus 1.
Okay.
I'm not sure if you could do that with trig functions, but
Well, what would your numerator look like?
Well, I mean, I'm not sure if you could use the cover-up method, but like you could do like for a like sine x equals 0, and then like you could use 0.
I mean, there are issues to doing that. So you just decide to go straight ahead and write this as a over sine x plus b over sine x plus 1 minus 1. Is that correct?
I don't know. I just treated it like if they were two different like factors.
Yeah, which is that's what you would get, right?
Yeah.
Technically, that would be incorrect. Because you would actually need a variable in the numerator here. With the trig functions, you'd want to go with something like a sine x plus b cosine x plus c over. So you want to actually generalize things a little bit more than that, which it's just not worth the effort. So no, you don't jump straight into partial fractions. To get partial fractions to work, to make sure that your numerator is usable and it follows from the simple strategy, that part is important. Okay, this is important for partial fractions. You need to be a rational function. If there is a sign there, it's not a rational function. Rational function means it's a ratio of polynomials. So now knowing that partial fractions works with a ratio of polynomials, what do you think?
I did a use of here.
Okay.
Where
U
u was
equals?
sine x and du was cosine x dx.
So you would end up with this du. Right? Now that's a rational function. Now I can follow the process that was described earlier. And in fact, here, this is something that I can do pretty quickly in my head with the cover-up method. Cover up the u, plug in 0, and cover up the u minus 1, plug in 1. The integral would be minus ln of u plus ln of the absolute value u minus 1. And here our u was sine x. So if you had just jumped directly into partial fractions, what you'd realize is that your numerators would be constants. And then you'd end up having to integrate 1 over sine x. You'd actually get the wrong answer. Because the integral of 1 over sine x isn't ln x. So yeah, you first have to convert things to rational functions. Very important to have rational functions, because then you have to worry about how your numerator is going to behave. And with polynomials, it's actually pretty easy to figure out how the numerators behave. So that was that one. First, do a substitution. This, incidentally, the same thing happened with the last problem. With the last problem, we had a bunch of exponentials. But the idea is, with a substitution, I could get that to look like a rational function. And so I guess an additional moral of the story is, don't forget your integration strategy. Once you see a new integral, you still run through that thing in your head. Is it a basic rule? Can I simplify it to be a basic rule? Would a substitution work? So you still should be thinking all these things before you even try to apply a partial fractions. And so right here, you'd realize that, you know what, because of that cosine in the numerator, a substitution would actually be a wise thing to do. And after doing that, you'd realize, oh, now I get a rational function. How do I proceed? You go through the process again. Is it a basic rule that I'm looking at? Can I simplify it to look at a basic rule? Can a substitution work? Well, I already did a substitution, so what are my options now? Well, it's a rational function, so probably partial fractions would work, right? Denominator factors, everything's hunky-dory. And by the way, so on Thursday, I would finish the last integration technique I want to do with you guys. And at which point I'd also probably wrap up that class. I don't know if this will spill into the next class, but I'll wrap that class up with just like an overall strategy for integrals. Like, how do you actually go through and decide what should I do to attack this random integral that's in front of me? And the first three steps are always the same. It's always the ones that I told you. As for how to move on further, whether it's by parts or by partial fractions or trig sub or whatever, I'm actually going to tell you what you should look for to actually know which is what. Now, this is actually a problem that we have seen before. I opened the last class with this because there was a very similar homework problem to this that was in the trig substitution section. So yes, technically speaking, you could do a trig sub on this guy. However, you'd be working a lot harder than you have to. So I actually already spoke about the strategy for this one here. So if I saw something like this, again, I would go through the same thought process. Is this a basic rule? No. Can I simplify this to be a basic rule? Not really. Would a substitution work? Interesting. If I were to substitute, I'd want to substitute what's under the radical because that clearly is making things complicated. If that radical wasn't there, everything would be fine. So I would do something like a u equals 1 plus x squared. However, because of the radical, let's actually throw on a square on that u to get rid of the radical at the same time. Why not? Now I differentiate both sides because we have to figure out what dx is. So I end up with u du is equal to x dx. Now you might be worried that, oh, well, I don't really see an x dx. However, I can multiply and divide by x to actually get my x dx in there. So now this part here, the x dx, that is your u du. The x times x, well, that's just x squared. This becomes u squared minus 1. And this part here is just u based on the substitution. Applying all of these guys, I would end up with the integral of u squared divided by u squared minus 1 du. And that is something that we learned how to break up with partial fractions earlier this lecture. I would subtract 1 and add 1. I would end up with this guy, factor the denominator. And then I would break that up. And then cover up the u minus 1, plug in 1, I would get a half. Cover up the u plus 1, plug in minus 1, I would get minus a half. And I can immediately start integrating. So that's u plus a half ln of u minus 1 in absolute values minus a half ln of u plus 1. And I think that's right. It's funny how I can be sleep deprived and my arithmetic suffers, like I'm getting 3/16 when I should have gotten like 3/8 or something, and yet I can like do partial fractions in my head and get it right anyway. Yeah, I'm telling you, algebra is the hard part. It's not the calculus, the algebra. Oh, and arithmetic. Okay. Yeah. I think a part of it too is like whenever I'm doing like arithmetic, my brain just kind of semi shuts down because it just gets so bored. Okay. F. Okay. What did we do here?
I did the P over Q thing so I could factor the denominator. I think it's like the rational root something.
Oh, rational roots theorem.
That one, yeah. The P over Q.
So you wanted to try to factor the x cubed plus 3x minus 4. So what you can do is the rational roots theorem. You can decide to try the factors of the constant term. Well, technically it's the factors of the constant term divided by the factors of the leading term. So in this case, you'll try to plug in x equals 1, minus 1, x equals 2, minus 2, x equals 4, minus 4. See if you get 0. Whatever, if your x equals a gives you 0 in the denominator, then you can actually divide this by x minus a using long division, and that will actually help you factor this guy. This is true. It's also overkill for this problem. So that might work out, probably. I don't know, but not necessary. Other options. So this is a random integral. What do we think first?
Could you use long division?
Long division of what?
Like the denominator by the numerator to get like 1 plus, like we did before?
When do we do that? Like when is long division an option? Like when would you think to do long division of the denominator into the numerator?
If you can't figure out how to do it algebraically to get the numerator and denominator to be the same, so you could simplify them to 1.
No, kind of you're close, you're getting warmer, but not really. Like this is important to know when we should actually try something. Like you would not try to do long division here, and I want to see if you guys can see why.
Is it because the power on the denominator is bigger, so it like wouldn't multiply?
It's
into
already
the first term?
bigger. The reason you would do a long division is if you have a non-proper rational function, meaning you see that the numerator has a degree higher than the denominator, higher than or equal to than the denominator. That's when you would think of doing long division. Here, the numerator is actually of smaller degree than the denominator, so I wouldn't actually divide them into it. I also mentioned that factoring the denominator, you can get it done. It's overkill here. You don't actually need it. So let's go back to our, yeah.
Would you do a U substitution and then multiply by 3 on the top and put a 1/3 outside the radical? Not the radical, the integral.
Okay, so your U would be what?
U would be x cubed plus 3x minus 4, which means du would be 3x squared plus 3. So if you multiply the numerator by 3 and put a 1/3 on the outside, then that ought to work, I think.
You factor out a 3, and look at that. You have this guy here, which is that guy there. So a substitution would actually work. What I just need is a 1/3 out here. And that's my guy. X cubed plus 3x minus 4. Okay, so that was a guy that I threw in here to kind of see, to slowly lead you into the fact that, yeah, I might just throw in an integral where you don't even need a partial fractions or a long division, just to see if you're paying attention to the overall strategy. This is a random integral. You always think along the same lines. Is it a basic rule? Can I simplify it to look like a basic rule? Would a substitution work? Your mind should have thought substitution before you worried about, can I do a by parts? Can I long division this? Can I do that? Like you guys are going too far, too fast. Start with the basics, start from step 1, work your way down. You'd realize that this is a substitution problem. Okay? So it looked messy and it looked complicated, but really it was just a substitution. And you just had to factor out a 3 to get it to work nicely. Or in your case, multiply by a 3 and divide by a 3 and just to fix it. So that was actually a straight up substitution problem. Nothing fancy. This one though did require something like what was suggested before. And of course, I mean, you could. Now, it is worth mentioning that if you did go along and factor the denominator, your answer would look like a bunch of ln's, but you should realize that you can actually combine these guys into one big ln. You'll notice that the answer you got is a sum of ln's, where when you combine them and you multiply the things being ln, it multiplies back out to the original polynomial. So you'd realize, yeah, you'd get the answer, but with much more work than is necessary. I mean, this shouldn't take you too long. However, this one, Had I tried the same trick, had I think substitution, like last time, I would say, well, obviously I'd want to substitute the denominator, right? That's just a basic substitution strategy. Your du here would be 3x squared minus 2. And doesn't, not helpful. So you could think, maybe I can split it into two parts. Maybe I can add 2x squared and then just move this guy over. But then you'd realize that you'd kind of end up in the same situation. Your substitution is not going to work out for the second integral. So this is one where factoring the denominator would actually help, right? And that was the hint that I gave you, because if I didn't tell you, it would probably be kind of hard for you to see that that's what you had to do here. So I just was nice and gave you that hint. However, here, I do expect you to see a substitution. Like that's something that I would throw on a quiz and not give a hint that, oh, it's a substitution. I'd expect you to actually pick up on that. It's a little bit harder to pick up on what to do here. So I would actually just give you a hint here. So now when you want to factor the denominator, it actually looks very similar to the first one. However, it's a cubic, which means you can't use the AC method or any of your quadratic strategies. It's not going to work. So now is where you would come into something like the rational roots theorem and how to actually use that. So let's actually do that. So let's factor the denominator. This is x cubed minus 2x minus 4. So tell me how this works, just as a reminder. So technically, this is something that you would have learned in pre-calc, and so I don't really want to go over it, but hopefully by just going through this example, you guys will actually remember how you did this. So maybe someone can remind me, rational roots theorem here, or factor, how did you factor this?
Last term divided by first term, and then put all those options as either positive or negative, and then kind of just guess until it works.
So you have a 1 in front here. That's a really squiggly one. You have a 1 in front here. So you look at the factors of constant term over factors of leading coefficient. Plus or minus, and you're going to try all these. What do I mean by try them? You're going to literally plug them in. So in other words, you are going to try x equals, you can have plus or minus 1, you can have plus or minus 2, you can have plus or minus 4, and plug in to see who gives you 0. Okay. Anyone you can see here giving you 0? Like a 2 seems like it would work. If I plug in 2, I would get 8 minus 4 minus 4. So x equals 2 is a root, which means x minus 2 is a factor, right? So if you plug in x equals 2, you get 0. That means if you were to factor this cubic, there should be a factor of x minus 2 times something else, so that when you plug in the 2, you get 0. What that means is that x minus 2 is going to divide into this cubic evenly. So this means x minus 2 divides into x cubed minus 2x minus 4. evenly. So at this point, you can pull out the big guns. You can pull out your long division. So you put your x cubed. You leave a space for the x squared. You would have a minus 2x, and then you'd have a minus 4. Okay, and so what do you get?
I got x minus 2 times x squared plus 2x plus 2.
Right, so you take the x into the x cubed. That leaves you with x squared. Take the x squared, multiply everyone on the left, the x minus 2. You would get x cubed minus 2x squared. You subtract that. This will give you 2x squared. X into 2x squared goes plus 2x. 2x times the x minus 2, you get 2x squared minus 4x. Subtract that. Minus 2 plus 4x gives me plus 2x. X into 2x goes plus 2. 2 times that guy, 2x minus 4. Subtract that. Minus 4 plus 4 gives you 0, and you should get 0 here.
Couldn't you do this a lot easier with synthetic division?
I don't know about easier, but synthetic division is equivalent in some cases. Personally, I don't like synthetic division as a personal preference because there are cases where it doesn't work, where so synthetic division, it only works if you're dividing by a linear term, which I guess is okay here. If you want to divide like a cubic by a quadratic, synthetic division isn't going to work, whereas long division still will.
Okay, I just wanted to check because that's how I learned rational rate theorem. Yeah,
I mean, it's equivalent. It's equivalent whenever you're dividing by a linear term to use synthetic division or long division. I'm biased towards long division because that's what I learned back in the day. And then when I learned synthetic division, I was like, that's kind of weird. And then on top of it, I learned it doesn't work in all cases. Like, screw this, I'm going back to long division. Okay, so now what you realize is that this means that if I take the x cubed minus the 2x minus the 4 and I divide it by x minus 2, I get x squared plus 2x plus 2 with 0 remainder. This means that my x cubed minus 2x minus 4 equals x minus 2 times x squared plus 2x plus 2. So that is what this exercise taught us. Okay, so now I can go back to the original integral. So the original integral had x squared minus 2x minus 2 now I know that the denominator factors into this. Okay, so we're done with the hint. Now what do we do?
Could you add 4x plus 4 to the numerator and then subtract it out again to get one of the factors to cancel out with the denominator? Like algebraic manipulation.
Oh, sorry. I'm bugging again. That's what we have. So that's what we have. Or reassess?
Yeah, so then you would add back 3x and add 4, and then you could also subtract it in the same numerator to get the
thinking too complicated. Too complicated. Think simpler. X squared minus x minus 2. Can you tell me anything about that?
It factors into x minus 2 and x plus 1, so you get a cancel.
Okay, so now we have that. Okay, can we finish it up? So we have a new integral. What do we do when we see a new integral?
Here I did u substitution,
Okay,
where my
So-
u was x squared plus 2x plus 2, and then I put a 1/2 on the outside of the integral.
right. So at the new integral, so you go through the process over again. Is it a basic rule? Can I simplify it to be a basic rule? Would a substitution work? At this point, we've simplified things as much as possible. We've already went through the long division, all that stuff. So it is already simplified. We already did the simplification step. So now the next thing is substitution. And so the substitution does work. So this gives us 1/2 times the integral of 1 over u du. And so that's 1/2 ln of the absolute value of u plus c. And so we have 1/2 ln of x squared plus 2x plus 2. And there we have it. That's the last problem. Now, on a quiz, would I give you a problem that's that involved? No. Would I give you a problem on a test that's involved? Unlikely. Would I put a problem on a final that is this involved? Probably. However, I wouldn't put other parts with that problem. So this will just be a standalone problem. However, that being said, even though you're very unlikely to encounter a problem of this level of difficulty, it's still actually good to actually go through it, because once you can maintain your focus and you can maintain going over a strategy over and over in your head for a problem that's very challenging and difficult and long, then the quizzes and tests are going to be like a step down. You only need like half the focus, right? So you could even have a semi-bad night and you can still perform well. So doing problems like these, still very important. Going through the homework, still very important. But if you're worried about, oh my God, on the quiz on Friday, am I going to need to know how to do all this? No, technically not. What I'm more interested in the quizzes is, yes, can you do the basic manipulations? Yes, but it's more important to me on the quiz that you actually know the strategies. Like, what is the approach for this integral? Like, how would I know what to do had no one given me any hints, right? That's the important thing, right? Now, on Thursday, I'm going to cover the last integration technique with you, and then I will have that discussion with you as well. How do you actually approach this integral? How do I know what to do? Like, if you never gave me a hint, like, how would I have figured out that I had to go through all this to get this problem done? How did I know here that I needed a substitution would have worked instead of me trying to factor the denominator and do a partial fractions? Like, how would you know not to end up wasting your time? That's actually just as important. And that we will deal with on Thursday after we do the last integration technique. Last integration technique I'm going to go over was something that debuted on the quiz last week. This is called the Weierstrass substitution. I mean, you can read into it if you'd like, but it should be pretty straightforward, I think. That being said, to get the Weierstrass substitution to work out, you do need to usually know all your techniques before that. So go over all the integration techniques that we've been doing. Make sure you know your substitution, your partial fractions, your basic formulas. That will make things go by a lot smoother on Thursdays. As for now, we are pretty much over time already, so I will let you guys go.
Thank you.
So
Thanks.
that being said, let us actually stop there. Thank you for your attention. Thank you for joining. I will see you guys later. I will see you in office hours, person who sent me the chat, and we'll stop right there. Okay, take care. Good
Thanks, Professor.
night, everyone.